Carolyn and I will be presenting today on Surface-Enhanced Raman Spectroscopy as a diagnostic tool. One of the reasons that this experiment has real-world applications right now is because normal diagnostic processes take a long time, to tell someone that they have a disease. And this was obviously a really big issue when we were going through the COVID-19 pandemic. If your diagnostic process, like when they were using PCR tests, if that takes a long time, then it can increase the spread of disease. So there's a real need to look for ways to decrease that process. Surface-enhanced Raman spectroscopy is a short, non-invasive optical technique that can be used to detect biological molecules in people's spit to tell them if they have a disease or not. This molecule right here is the one we were testing for. It's called pyocyanin, and it is a biomarker for an antibiotic-resistant bacteria. So we can use it as a model to show how this technique can be used on other diseases.
Okay, for the basics of Raman spectroscopy and surface-enhanced Raman spectroscopy, we're going to first try and understand briefly what the main idea of Raman spectroscopy is. So it is a chemical analysis technique that combines the interaction between light and chemical bonds and uses it to detect different chemical makeup. So when a laser hits a material, three different things can happen. The light can be transmitted, it can be absorbed, or it can be scattered. Additionally, when it's scattered, it can either be elastically scattered or inelastically scattered. Raman scattering is this inelastic scattering. The elastic scattering is something called Rayleigh scattering, which we will not be focusing on. So basically, when light is inelastically scattered or Raman scattered, it's the light hits your molecule, and the atoms within these molecules are at the ground energy state, or a higher energy state, and the molecules are sent to a virtual state very briefly before falling back down to either the ground state or an energy state. So if it starts out at the ground state, is sent to this virtual state, and then comes to a higher energy state, it's something called Stokes scattering, which is what we'll be focusing on. And then anti-Stokes scattering is when it starts out at a vibrational state, goes to this virtual state, goes down to the ground state. And that is anti-Stokes scattering. And that does not happen really at room temperature, so we will not be focusing on this. But when this scattering happens, it causes the light to have a different energy and a different frequency than the incident light. And Raman spectroscopy detects these shifts called Raman shifts. Your shifts in intensity are what this detector is monitoring. And each chemical molecular compound has different Raman shifts, and this serves as a fingerprint, and it is unique for every makeup. So that's the basics. And here's a diagram. It shows, these vibrational states going to a virtual state and then coming back down, and it shows what this shift looks like. There are different peaks in a graph. So for surface-enhanced Raman spectroscopy, a difficulty with non-surface-enhanced Raman spectroscopy is that it's very weak intensities that it can detect, and it has a difficult time differentiating between closely related molecular structures because their intensities are just too weak. Surface-enhanced Raman spectroscopy amplifies this Raman scattering signal by very large factors, making it easier to detect. And it works by adhering molecules two nanostructured metallic surfaces, typically gold or silver. We use silver for our purposes, but these metallic surfaces allow for surface plasmon resonance, which is vibrations of free electrons. And these vibrations cause an intense electric field near these molecules, which then boosts the Raman signal. And because of this enhanced detection, you can monitor and detect very, very low concentration of molecular structures, which is useful in our lab. Okay. And here's a couple diagrams. You can see in the one on my right that you have your gold metal particles or silver. The laser hits the analyte, and it causes a hotspot or these increased areas of the electric field, and then it sends that surge signal. Okay, for our setup, the Raman spectrometer we use is the Renishaw InVia system. It has two choices of lasers. You can have one with 512 nanometer wavelengths or 785. We use 785 in our lab, and basically how the spectrometer works is you have your laser. It is shown into the machine where it is then reflected and then Brawley filtered, and it is then sent, the light is sent to your sample, which then sends a signal back that is then filtered through the Rayleigh filter, is reflected, sent through the Rayleigh filter, which filters out all those, all the elastic scattering we talked about earlier, because the intensity is much stronger than Raman scattering, so you want to filter all of that out. It is sent through a slit, and then an optical grating where it is separated into its different wavelengths, and then sent to a CCD camera, which is connected to a computer, which, you know, gives us a graph of all the peaks from our spectra. For our experiment, we are using SIRS to detect pyocyanin, which is a biomarker of Pseudomonas aeruginosa, which is a bacteria that can cause illness in the blood, lungs, other parts of the body, is present in people with cystic fibrosis, pneumonia, and is very dangerous for immunocompromised people and requires fast, accurate testing because it can be very antibiotic-resistant, and so you want to start treatment as soon as possible, especially for those people that are immunocompromised. So at the bottom of this PowerPoint, you can see the pyocyanin makeup and then just a picture of the bacterium. So moving on to methods. For our purposes, the PCN samples were diluted into various concentrations using the DMEM buffer. These concentrations were then dispensed onto silver nanorod substrates for 30 minutes before being cleaned with deionized water and set out to air dry at 20 degrees Celsius. Once all of these different concentrations were ready, they were each individually placed into the Raman spectrometer, and the SIRS spectra were collected by this confocal Raman microscope. The laser power was set to be 9 milliwatts at the sample and 5 times the objective lens with 10 seconds of acquisition time. And if you don't know, this machine is basically, there's a microscope and then the whole machine as we saw in the diagram. And on the outside of the machine, there is a computer that is connected to a camera inside the spectrometer, and you can see your sample, you can focus and adjust the microscope as needed before closing the door, and then hitting run on the computer, and it collects all your spectra for you. So yeah, that's it.
Okay, so while we were processing our data, we used a couple of programs. We used Spectra Guru, which is a website made by Dr. Zhao's lab group, which is very cool. We used Origin Pro and we used Excel, and I'll specify which program was used to make each figure as we go along. And this is Carolyn using Spectra Guru in the Riverbend lab. Okay, so this, as we talked about earlier, we took 41 different spectrums in 41 different positions over the substrate for each of 6 concentrations. So all these spectra are from different positions on a substrate with a concentration of PCN of 6.67 times 10 to the negative 2 milligrams per milliliter. And so the steps we took to process this were, first, we cropped it from about 400 to 1800 wave numbers. We baseline normalized it, which we basically took it so that the noise fluctuates around zero intensity. We smoothened it, and then we averaged it. So this dark blue line, this is the spectrum that we'll take into the rest of the data processing. This is the process we used for the 3 largest concentrations of PCN. For the 3 smallest concentrations, we used a different process. This is the smallest concentration of PCN we had. This is 5.21 times 10 to the negative 4 milligrams per milliliter. As you can see, it's incredibly noisy. It's got lots of weird spikes going on. So the process was a little bit different here. So first we cropped it around 400 to 1800, same as before. And then we despiked it, which this could have been a cause of issues, which we'll discuss more later. But this is after it was despiked, and it was baseline normalized again, so it fluctuates around 0. It was smoothened, averaged, and this dark blue line is what we'll take into the next steps of data processing for this smallest concentration. Okay, so these 2 graphs were both made using Origin Pro. And this one on the right shows actual intensity for each concentration, which is listed here across the whole spectrum. And this graph on the right shows the relative intensity of each spectrum compared to each other based on their concentration. So you can see that this is the greatest concentration down here, and the spectrum is a lot more relatively intense than the spectrum at the top, which has a much lower concentration. And then this graph was made in Excel, and it shows the relationship between concentration of PCN versus intensity. And we made this graph by picking out this peak right here, the left one of the double peaks, and we found its coordinate, and we wrote down its intensity at this top peak right here, and then we graphed that versus concentration, and found that the relationship was, it fit a linear curve very well. These graphs show very clearly that the spectra decrease in relative intensity as concentration decreases, but it does maintain its shape, its molecular fingerprint that can be used to identify the molecules. So the PCN is always identifiable. If we want to look specifically at peaks in here, if we look at this point on the left, as concentration decreases as we go up the figure, it does get a little bit noisier, especially right at the top. It's hard to distinguish signal from noise up here at low intensities and low concentrations, just because like the intensity it's not that much bigger than the noise, so that could prove to be an issue, and that's something that probably needs to be worked on. Or if you look on this side, like the double peak looks fairly standard in the first 3, and then they sort of start switching heights as you keep going down in concentration. It also gets wider, it gets less sharp, and this is more issues with noise when the intensity is really low. So the relationship for all of the concentrations we tested does appear to fit a linear curve very well. And this would indicate that if we tested the spectrum of a concentration twice as high as our highest concentration, then we should be seeing approximately twice as high relative intensity of the spectrum. So I mean, clearly it's easier to detect PCN when the concentration is larger, because of how low the intensity is here and just how easy it is to get confused with noise. Um, so in conclusion, we seem to have found a very clear correlation between the concentration of PCN and the intensity of the spectrum, which indicates that surface enhancing Raman spectroscopy could be a very useful tool for diagnosing people with illnesses. I did say I'd talk about despiking later. One of Dr. Zhao's students did say that the website had been having issues with despiking, so there is a possibility that on our 3 lowest concentrations where we used that tool, we could have introduced more error into the results of this experiment. So that is something to take into consideration. When we think about the usefulness of surface enhancing Raman spectroscopy for diagnosing illnesses, it seems like, at least based on this, that would depend on how discerning the equipment is and how good it is at filtering out noise at lower concentrations, because while this does look pretty good compared to the rest of the spectra, it is like it doesn't look exactly the same. So if the equipment you're using isn't very good at filtering out noise, that could be an issue if the person isn't very sick. Yeah, and these are our sources. Thank you so much for listening to our presentation.